Welcome back to our channel Circuit Masterclass, where we break down the complex world of electrical engineering into simple, powerful insights. Whether you're a student, a budding engineer, or just curious about how electricity shapes our world, you're in the right place. Let's have a discussion on the vacuum interrupter. We shall cover the constructional details of a vacuum interrupter along with its function, how it facilitates arc quenching, and more. Okay, before diving into the detailed discussion about the vacuum interrupter, let us first look at the basic concept of vacuum circuit breakers. A vacuum interrupter, which we also call a VI for short, is the key component of a vacuum circuit breaker or VCB. In a vacuum circuit breaker, the arc quenching takes place in a vacuum. No medium like air, oil, or sulfur hexafluoride gas is used for this purpose. In a vacuum, there is no medium present. Hence, no ionized particles in the gap between the breaker contacts. Suppose this is a fixed contact and this is a moving contact. Let's say the moving contact is retracting. This means the contacts are getting separated. If this separation occurs for the interruption of current, the atoms between the contacts get ionized due to the high voltage gradient between the opening contacts. As a result, a channel of ionized particles forms, helping to continue the current even though the contacts are physically separated. This is because, as we know, an ionized medium is a good conductor of electric current. Now, you might think that due to the absence of a medium, there should be no such phenomenon, and hence the current should be interrupted without any arc formation. That is, the interruption would be absolutely instantaneous. But this can be problematic for the system because a sudden drop in current is essentially current chopping. As you know, current chopping is dangerous for an electrical system. However, we are fortunate that vacuum arcing phenomena do occur, though in a different way. In a vacuum, when two contacts separate, a hot spot is created at the last point of contact surface separation. Let us elaborate on this concept for better understanding. When two surfaces detach from face-to-face contact, the separation is not instantaneous. Instead, the contact area reduces gradually to a point before finally separating. At that last moment of detachment, the entire current tries to flow through that narrowest path. This generates a hot spot. As the surrounding environment is a vacuum, the metal at the contact surfaces near the hot spot vaporizes easily. This metal vapor, due to its free electrons, helps to continue the current by forming arc plasma. During the zero crossing point of the current waveform, the vapor condenses. Let us see the waveform. Say, at this instant, the moving contact gets completely separated from the fixed contact. The current still continues due to the metal vapor arc. This is the first zero crossing. Here, the current becomes zero, causing the metal vapor to cool and condense. For the next half cycle, there will be no metal vapor left to sustain the arc as it has already condensed. However, practically, due to restriking voltage, the arcing may continue for 1 or 2 more cycles. Okay, let us come back to the actual topic. A vacuum interrupter, or VI, is a vacuum chamber within the vacuum circuit breaker where all of this happens during the operation of the CB. The image on the screen shows the VI. It is actually a removable part of the VCB. It is to be fitted into the CB mechanism. Being a replaceable part, it can be swapped with a new one when needed. This is a 3-phase outdoor type 36 kilovolt vacuum circuit breaker. If we look into any of the poles, we shall see an interrupter fitted inside. This interrupter must maintain a vacuum, facilitate the smooth movement of the moving contact while preserving the vacuum, maintain insulation between contacts when the CB is open, and handle metal vapor during live operations. Each part serves a specific purpose. Let us explain them one by one. First, observe the white portion. This is an insulation cylinder made of hard ceramic. It consists of two parts, upper and lower. These two parts are joined at the center by a stainless steel contact shield. I shall explain the purpose of the contact shield shortly, but for now, let's focus on the ceramic cylinder. It forms the main container. It must withstand the vacuum and hence must be strong. It must also withstand the system's basic insulation level, that is, power frequency withstand voltage and lightning impulse voltage. Therefore, this part of the vacuum interrupter must be both mechanically strong and have a high insulation level. Now let's come to the contacts. This is the fixed contact. This metal cover flange holds the fixed contact. The joint between the fixed contact and this bottom cover is hermetically sealed. The cover is normally made of hard steel and is attached to the bottom ceramic cylinder. The joint with the ceramic cylinder is also hermetically sealed. This fixed contact is made of a copper-chromium alloy. Adding chromium to copper slightly reduces conductivity, but it is essential for controlling and maintaining the quantity of metal vapor. This is the moving contact, also made of the same chromium-copper alloy. The upper portion, meaning this part of the contact, is connected to a steel bellow. The bellow is hermetically sealed with the upper steel cover, which is mounted on top of the upper ceramic cylinder. All of these, bellow, moving contact, top steel cover, and top ceramic cylinder, are hermetically sealed. The bellow is made of steel sheet. Its function is to allow the free movement of the moving contact. The lower portion of the bellow is protected with a steel cap to shield it from metal vapor. Now, let us move to the contact shield. This is the contact shield, made of non-magnetic material like stainless steel. To understand its function, imagine there is no shield around the contacts. Then, during each operation, some metal vapor may stick and condense on the inner wall of the ceramic cylinder. This would reduce the insulation property of the cylinder. Hence, there must be a mechanism to prevent metal deposition on the ceramic wall. That's precisely what the contact shield does. The vapor emitted during contact movement is captured by the shield, thereby protecting the insulation of the ceramic cylinder. The contacts shown on the screen are simple ones. These are called butt-type contacts. However, for better arc distribution across contact surfaces, several special designs are available, such as spiral type, radial slot type, axial magnetic field type, radial magnetic field type, and axial radial hybrid type. These designs ensure uniform arc distribution over the contact surface. Without them, localized arcing could erode the contacts, reducing the vacuum interrupter's lifespan. If you found this helpful, don't forget to like, subscribe, and tap the notification bell so you never miss a voltage boost from our channel. Got questions or want us to cover a specific topic? Drop it in the comments. We read everyone. Thanks for watching. And as always, stay grounded, stay curious, and keep engineering your future. See you in the next one.